solve problems that require use of Pythagorean theorem. We're also going to pick up a handful of geometry vocabulary terms that you need to know. You will be tested on them on your test, as well as they could be tested on the CST, so make sure that you are listening for when I run into a couple of vocabulary terms that may or may not be new to you, but are part of the design of what we need to learn today. All right, we're starting with this first problem. This first problem just gives us a triangle. We're being asked to find this value of the missing side. So we want to go ahead and label A, B, and C. I recognize my right angle here, so I know my legs make the L. So my A and my B are going to be the square root of 32 and this 7. It means I'm trying to solve for C. Plug into my equation, A squared plus B squared is equal to C squared. I get the square root of 32 squared plus 7 squared is equal to C squared. This next step is where we have to get a little bit more thoughtful about the work that we're doing. Think about some of the things that we've learned this year about the relationship between squaring something and taking the square root. Because we have the square root of 32 squared. Ricardo.
I think it stays the same.
Right, it's just going to be 32. Because what we see is that square root and squaring themselves are inverse operations. That's a lot like saying, hey, I've got a value, A, and we're adding 2, and then we're adding negative 2. Well, those two operations just cancel out. Same thing here, when we have something squared and we take the square root, those two operations just cancel each other out. Okay? Remember that taking the square root and squaring something are inverse operations, so they just undo each other. Questions about that? Andrea. So if you have something that is squared and taken the square root of, it's always just going to make those two operations disappear because they're inverse operations. So 7 squared is 49. It's only got the one operation on it, so that's the only one that we have to worry about. It's equal to C squared. 32 plus 49 is 81. Is equal to C squared. Here we see the use of that inverse operation that we use all the time. We have this square root, or we have that squared, so we take the square root of both sides. Here we see the inverse use of that. Square root and squared, they cancel out. That leaves us just the C. So you actually have been using that very same concept for a very long time. You just didn't recognize it. All right. Looking over the next one, this is where things are going to get a little bit more complicated. We're going to see a problem here. We see what is the length of the diagonal of the rectangle below. So the first thing that we see here is the word diagonal. This is one of those vocabulary terms that you have to pick up today. The diagonal of a shape is the furthest distance across the center of a shape. So here we see that we were given a rectangle. And so they're showing us the diagonal of this rectangle is this furthest distance across the center of the shape. Now that goes for three-dimensional shapes as well. So not that we will be using any problems today that have three-dimensional shapes, but for instance, if we had a rectangular prism, a diagonal would be the furthest distance across the shape. The furthest distance is not from across a face, it goes all the way through the center of the shape, all the way through the center of the shape. So it would go from the top left all the way to the bottom right, which would go through the center of the shape. And I know that's kind of hard to think about, but it's not along any of the faces. If we're talking about a three-dimensional shape, the diagonal is going to go through the center of the three-dimensional shape. Isaiah.
So it's like you put in, you know how they got blocks? How you put the blocks together? So it's like that?
Very similar. All right. So let's look at what this problem is asking us to do, now that we understand what a diagonal is. All right, so it's asking us to find the length of the diagonal, which we have here in blue, of this rectangle. So at this point, the only thing that we can really do here is we see that this rectangle with the diagonal in there has been broken up into two right triangles. So we just need to pick one of those right triangles that we can use. I'm just going to choose this one. And this is something that I'm going to expect you to do as part of your work. Whenever you're going to use Pythagorean Theorem in a shape that is more than just the right triangle you're using Pythagorean Theorem for, I expect you to outline it like this. That way you're just absolutely clear on what you're doing. I'm going to go ahead and label A, B, and C. So this would be the A of my triangle, this would be the B of my triangle, and this would be the C of my triangle. So the diagonal is the unknown. And it also, though, looks like A is unknown. So what I see here is that it looks like I don't know my A. But is there some other thing that we can think about, some other piece of geometry knowledge that we can use to determine how long A is? Nafisa?
I don't know how to explain it like in the right way, but in the tracks, like how you see 44 squared, it's like the same shape, so you know that it would be like, so you can use the same number.
So Nafisa is making the assumption that these are the shapes are the same and that this is the square root of 44. The reason we can make that assumption is because they tell us that this is a rectangle, and we know that all rectangles have opposite sides that are equal. So this side over here is going to be the same as this side over here. So that's why we can make that assumption. All right? So now we look at our Pythagorean theorem, because we've got two of our three sides. So A was the square root of 44 squared, plus B squared would be 12 squared. Is equal to C squared. The square root of 44 squared is what, Damien? Louder? 44. Those operations just undo each other. 12 squared is what, Mr. Matlock? Is 144. We add those together, we get 188 is equal to C squared. And then here we use that inverse operation of squaring and square root to get our C alone. Make sure we do it to both sides, and we get that the square root of 188 is equal to C. So the distance here of our diagonal is the square root of 188, and here we have units, so let's go ahead and put those units on there. Square root of 188 inches. All right, so sometimes we can use Pythagorean theorem to help find out things about larger shapes that have right triangles in them. Next one, it says a line segment BD bisects. So we have this word here. We're going to break that down. Bi meaning two, sect meaning kind of cut. So it's cutting it. In particular, we know this word also means that it just doesn't cut it in two, it cuts it into two equal parts. So that's our definition for this word. Make sure that you have that down. Bisect means to cut into two equal parts. Trisect would mean it would cut into three equal parts. So this is a vocabulary term that you need to know. in terms of our geometry. And we're going to be using that piece of information here pretty soon as well. Line segment BD, so this is talking about BD bisects AC, so it cuts AC directly in half. So what does that tell us about the different parts of this line segment? It means AD and DC are what? If it is bisecting, that means AD and DC are what? What do we know about AD and DC? Winter? They're not parallel. Well, they're on the same line. So if they're bisected, in other words, they're cut into two equal parts, that gives us a little bit of information about them. Andrea? Yeah, that they're 15, because we see the whole thing was supposed to be 30. So that means the parts of it, since it's bisected, are also 15. All right. It also goes on to further say that point D is the midpoint of AC. That's actually just repeating for us what we already know. A midpoint means that is exactly halfway. Which means that that particular point also cuts that line segment directly in half. So it tells us the same thing, that point D cuts this line directly in half, which again tells us that each of those two parts is 15 meters. The question asks us, what is the height of the triangle? So as I'm looking at the height of the triangle, I know that this is what I'm trying to find. So the only two things we really know to do with trying to find the missing parts of a triangle is to use right triangles. So the only two right triangles I have right triangles on the left-hand side, on the right-hand side. So this is the right triangle that I'm going to use. This is why I'm outlining it, because I'm not using the entire triangle. I can't use the entire triangle because the entire triangle is not a right triangle. So I have to cut out this piece that is a right triangle. Thanks to the information that's given to us, we can see that we don't know our A. Thanks to us knowing what a midpoint was and what it means to bisect something, we know that B is 15 meters. And we know C is equal to 25 meters. So we have A squared plus B squared is equal to C squared. A squared we don't know. B is going to be 15 squared. And C is 25 squared. A squared plus 225 is equal to 625. Solve the equation by first adding the opposite. So we get that A is equal to 20. So we get the height of this triangle is equal to 20. I'm going back to my question, and I'm seeing it ask me for this height of this triangle. That's what we were really trying to figure out. In some of these equations, or some of these problems, it may ask you to do even more difficult things. For instance, this may ask us to find all missing parts of this triangle, including the height and this side, in which case we would have to use the information that we just got to do another Pythagorean theorem problem. All right, coming over here. This problem says the infield of a baseball diamond is a rotated square, as pictured below. There are 90 feet between each set of bases. The catcher throws the ball from home plate to second base. How far is the throw? So the first piece of information is that it tells us that this is a rotated square. What does that tell us? If it's a rotated square, what significant piece of information does that tell us?
If
William. Well, I mean, even if it was a rectangle, I could make it into two triangles. We've seen that already today. But there's something very specific that this is trying to tell us that it's a square. And that's not quite represented on the picture. Isaiah.
That all sides are equal.
All sides are equal, and it kind of shows us that in the picture. There's another important piece of information that we need to make sure that we absolutely know. Ricardo?
It's a sideways square.
That's what it tells us. Yes, it is a sideways square. Andrea? All of the angles are right angles, and that's really important for us because if we want to use Pythagorean theorem with these triangles, we have to know that they are right triangles. So that's really important for us to know, is that these are right angles. You can draw kind of diamond-looking shapes that don't have right angles. But what's important here in this particular shape is that we know that they are all right angles. And that's really important for us because that's what allows us to use Pythagorean theorem. So I'm going to pick a triangle.
Ooh, I like that triangle.
And I'm going to outline it, just like I've asked you to do. If you're using parts of larger shapes and you're using Pythagorean theorem, I want you to outline the part that you were using Pythagorean theorem for. I remember that my legs make my right angle, so in this particular triangle, this is my right angle, so these are my legs, A and B. And that means I'm solving for C. So I'm going to go ahead and write my equation down. A squared plus B squared is equal to C squared. Both my A and B are the same. 90 squared plus 90 squared is equal to C squared. This is 8,100 plus 8,100 is equal to C squared. Which means that we have 16,200 is equal to C squared. And we need to take the square root of both sides.
Yes.
So that square root of 16,200 is equal to C. Now, we would want to find out probably more specifically what the square root of 16,200 is, because if I tell the catcher that he is about to throw the ball the square root of 16,200 feet, he'll probably look at me like I have 3 heads, because that's not meaningful to him. One thing that we do know is that it must be at least how far?
90. No.
It must be at least 90, because we know the hypotenuse of a right triangle is always longer than the legs. So we know it must be at least 90. I will leave it to you as a part of your can-do. You can do this as your can-do in the can-do section of your alone time to figure out how far the actual distance is. But for now, we're going to go ahead and move on to our key points. Key points, por favor, please. Ricardo. Ricardo.
Oh, if there's a square root in a hypotenuse problem or a Pythagorean problem, then it stays the same.
So let's just make sure that we're a little bit more clear there. If you square a square root the operations just cancel. So as an example, if we have the square root of 6 and then we square it, that's just equal to 6. Questions about that? Key point number 2. By means to. So I think all of these particular terms, I think you should probably put stars next to all of these vocabulary terms. So when you're going back to study, you know to look for them. Diagonal is the furthest distance through a shape. I think putting a star next to all of those particular vocabulary terms, those are important things that you need to walk away with today. Are there any other key points that anybody would like to add in today? Furthest distance through a shape. All right, let's go ahead and move on to our together time.